Joe Nelson, Ning, Morgan Weiler, and Yirong Yang, who are going to tell us about symplectic embeddings.
Cool. So thanks so much for the introduction. So for those of you that don't know, I'm a professor at Rice, and this is my 3rd year at Rice. And my research is in symplectic topology, which combines a lot of subjects together. So a lot of times you'll see me teaching like many different classes, from analysis to topology to differential geometry. And then over the summer, I invited 2 undergrads, so that's Hao and Yirong, to join my postdoc, Dr. Morgan Weiler, and my grad student, Leo, to study symplectic embeddings using Hutchings' Beyond ECH methods. And I was desperate to come up with a fun name for the project, so we called it the virtual BeECH, for Beyond ECH. And so we'll start pretty easy with just what is the definition of a manifold, what are some kind of nice properties that they have, and then we'll move on to symplectic forms, and then give a brief overview of kind of embedding problems in symplectic geometry, and then the progress that we made, and then Hao and Yirong will also give a sketch of our proof. So I'll first start with the definition of a manifold, and there's a kind of terrible looking definition that you see like your first semester of a differential geometry class, and then you mostly forget about it, and you just remember that a manifold is a topological space that looks locally like Euclidean space Rn, and it admits a global differential structure. And if you haven't seen topology yet, that's just a way to define more general classes of open sets and to define continuous functions in terms of open sets. And so it allows you to work with spaces that are not as sort of rigid as Rn, and you can think of really exotic, cool spaces. But manifolds somehow they split the difference between topology and Euclidean space. So you get like the best of both worlds. And then the way that we define the smooth structure on this topological space is you need something called a smooth atlas. And so an atlas, like any other kind of atlas that we use for the world, consists of charts. And those are going to be a collection of open sets which cover your manifold X. And then they need to come with these maps phi I, which have to be diffeomorphisms onto open subsets of Rn. And in that way, you're able to go between sort of the manifold and open charts in Rn. And the transition maps, they look terrible, but basically it allows you to work with points in a manifold and open sets in a manifold, but you can convert them into just working with maps between Euclidean space. And so that's great because it means you can apply all of your favorite theorems from analysis and differential equations. It's just that you have to like go through a lot of pretty intense notation. But the upshot is that manifolds are sort of these nice differentiable objects in a particular sense that allows us to use and import all of our theorems from sort of analysis and differential equations. And I guess as an example of a manifold, you can have a sphere, so like a hollowed out orange, and then a charts for the sphere, your smooth atlas could be sort of the northern hemisphere that just covers below the equator. And then you can have the southern hemisphere, which just goes up past the equator. Their union will give you the sphere, their open sets, and then you can map sort of these, the north hemisphere to R2, and you can map the south hemisphere to R2 as well. And a more exciting example of a manifold is a Klein bottle. So a Klein bottle is related to, I guess it has a sister manifold, which is a donut. So a donut you form by taking a cylinder and you glue the edges to each other, but you don't mess up the orientations. So since this is a piece of paper and not a rubber sheet, we can't actually make a donut. But with a Klein bottle, what happens is you go around this circle, but you go around this circle in the opposite orientation when you glue them together. And as a result, you can't do this in 3 dimensions without self-intersection. And so you end up with this kind of like weird self-intersection. And these Klein bottles are examples of manifolds, even though they're not sitting inside of 4 dimensions as sort of a subspace. You could realize them in 3 dimensions as being immersed, but manifolds don't care about the fact that you can put them in a bigger Euclidean space. They can just kind of like exist in their own crazy way. And Klein bottles, they're kind of not really bottles, because if we look at this purple liquid, if we just turned the Klein bottle upside down, we could make it so that all the liquid fell out. And that's kind of counterintuitive, because if you had a donut and you filled it with jelly, you wouldn't be able to get the jelly out of the donut unless you took a bite into the donut. And so usually closed manifolds have a well-defined inside and an outside, but Klein bottles don't. They don't have an inside or an outside. And that's because they're the higher dimensional generalization of a Mobius strip. So a Mobius strip you get by just taking a strip and you glue this piece to this piece with opposite orientations, you get a twist. And so a Klein bottle is actually, if you were to take two Mobius strips and glue them along their common boundary, you would end up with a Klein bottle. But it's not a very, it's a pretty difficult thing to check, as Yirong can tell you. And okay, great. So here's an example of a more exciting manifold, and it's not embedded. And so we're going to talk about embeddings later on. And embeddings just basically mean that we have things that act like subspaces, the way we think about subspaces in linear algebra, subspaces in topology, subspaces in in topology, geometry, and linear algebra. So these are not examples of embedded manifolds, so they don't have sort of this nice subspace topology. So what's the other sort of part of differential geometry in the study of manifolds is that we have all these like crazy abstract definitions, but then it turns out that at the end of the day, it's actually isomorphic to sort of a common, it's a commonly identifiable object, but you just have to go through all these crazy definitions and you're like, oh, but I was just talking about a vector space, which was Rn. Seriously, we had to do 20 pages to like define the tangent space to a manifold, but it's what you have to do. So a tangent space to a manifold is going to be a vector space that consists of all the sort of possible directions you can move. Those would be like your velocity initial vectors. So it kind of intuitively consists of all the possible directions in which tangentially you can pass through the manifold. And as a result, you end up with a space that's diffeomorphic to Euclidean space of the same size dimension as the manifold. And what's great about the tangent space is that to every point, we have a linear space that we can associate to the manifold. And so that allows us to think about linear algebra in a very useful way. And we can import basically everything we know about linear algebra, because if we have a smooth map between two manifolds, it turns out if we look at its derivative goes from the tangent space of the first manifold to the tangent space of the image of that point in the second manifold. But those are just linear subspaces. And if we evaluate the differential of the function at the point P, we're just going to end up with some matrix. And so we can think of kind of derivatives in terms of linear transformations once we go down to evaluate things at points. And once we start talking about linear spaces, we can talk about linear functions or multilinear functions. And so that's where the notion of differential forms show up. And so a one form, that's just a linear function that takes something from a vector space. And so in this case, it's going to eat a vector that's sitting at the point P, and it spits out some number. So you've already seen a couple of one forms before in your life. It's just that they were probably not called one forms. So if you've had multivariable calculus, you may be familiar with the notion of a directional derivative. So you take the gradient of the function, so that's sort of the derivative in each of the coordinate directions. You can evaluate it at a point that gives you a vector, and then you can dot it with the direction in which you're supposed to differentiate. And that's you get by taking the vector divided by its norm, so that you're looking at a unit vector. So it turns out that you can kind of make sense of a directional derivative in the land of manifolds, but you have to be a little bit more careful. And this dot product is actually something that's called a Riemannian. It's an example of a Riemannian metric. And in Riemannian geometry, you end up studying sort of angles because you have this ability to look at things like inner products. But another sort of way that forms arise is in terms of integrands. And so actually differential forms are sort of the preferred thing to integrate, because you don't have to talk about coordinates when you talk about differential forms. You can define them abstractly because of how you've abstractly defined the tangent space. And so you don't have to talk about like parametrizations, and you can write down really nice facts about integrals. And as a result, you can think of when you do a line integral, so that's doing the FDS, that FDS is actually an example of a one form. It's just that normally you don't encounter one forms in the wild before you're a graduate student. You only ever sort of see one forms or two forms or n forms that you're integrating, because that's kind of the natural context in which you integrate forms and why kind of differential forms arose. And then when you take a class in differential geometry, you get to find out that these things that you were integrating are actually something called forms, and that they exist more generally, and they have lots of great properties. And then the cute picture of a tangent space is an owl. So I was thinking, this is an undergraduate colloquium. I have to have some nice pictures. And I was like, oh, it's at Rice, so I'll find a picture of an owl. So I found this picture of an owl, and then I was like, it's blue and purple. These are my favorite colors. I have to buy this owl. But then I didn't know what size I should get the owl in. And so I got them in all the sizes. And I got owls for everyone in my research group so that they could always explain tangent spaces to manifolds. And it will turn out that that's really important, because we're going to talk about a symplectic form. And so a symplectic form is going to eat two vectors at a single point. So if we zoom in on the owl's head, we just pick out a sequin. If it's blue, it turns out that it has the opposite orientation than the purple sequin. And then you can talk about diffeomorphisms that preserve or reverse orientations, but we're not going to talk about that. Instead, we're going to zoom in on our sequin, and we would pick two different vectors, and we would input them into our two form. And it's called a two form because it can eat two vectors. And symplectic forms are a special class of two forms. And I'm going to hand it over to Leo to talk to us about symplectic forms and symplectic manifolds.
Okay, thanks, Joe. Yeah, so as Joe mentioned, what is a two form? At each point, we have a way to pair two vectors. So each point, I got my two pens here. It's a bilinear function, so it's linear in each component. And if you flip the order that you take the pairing, you'll flip the sign of the pairing. So that you have that at every single point in your manifold. You have this bilinear function on the tangent space. And a symplectic manifold is necessarily an even dimensional manifold that comes equipped with a two form that satisfies these two properties that we see. So the first property is a closedness property. So if you know what the exterior derivative of a form is, this essentially tells you that as a three form, its exterior derivative is 0. But the other property that is maybe easier to understand at face value is the non-degeneracy condition. So there's two ways to state it. You can take the n-fold wedge product of the two form with itself, and you'll get something non-zero. But another way to say it, and this is how Sue Tolman explained it when she came to Rice last year, which was kind of nice. Every non-zero vector has a friend. So at every single point and every non-zero vector, you can find a friend for which its pairing will give you a non-zero number. So non-degenerate is kind of referencing that. So we have two nice examples, the whole family of examples really. The first one is the plane. It's even dimensional. It works as a smooth manifold. It's not just a vector space, but it is a smooth manifold. And the two form that we have on it can be written in coordinates as dx wedge dy, and that's actually the area form. If you've ever done an integral on the plane before, that you've implicitly been using that area form to tell you what's actually happening, and that fits into a larger class of examples. The even dimensional Euclidean spaces are all symplectic manifolds, and in coordinates, that's how you would write the symplectic form, the standard symplectic form on this. And you should note that if you did take the n-fold wedge product of that sum there, the dxi wedge the dyi, you'll get a whole long sum, a single sum with a coefficient in front of it, and that's actually the volume form of R2n. So those are some examples. Thank you. And then, so here's some more examples, and these are kind of the examples of the symplectic manifolds that we'll be dealing with today. They're kind of simple in a certain sense, but we'll actually, the family that I just described, the Euclidean spaces R2n, can be reformulated in terms of complex coordinates. So Cn is an even dimensional manifold. And if you wanted to convert the previous two form in those coordinates, the dxi's and the dyi's, into complex coordinates, that sum that you see right there is how you'd write that two form. So that's our symplectic form on Cn. And we've got 4 examples of symplectic manifolds arising as subsets of Cn. So the first is, well, you can talk about the ball inside Cn, and be careful, it's not the ball of radius r. I like to say the ball of parameter r, because it has the property that if you slice it with any of the complex coordinate planes, you get a disk of area r. So just be careful it's not a radius there. Now the cylinder is also in Cn, and you obtain it by restricting that first component by taking values in the disk of area r, and you'll let all the other components range free. So that's the ball and the cylinder. And the next 2 set of examples are necessarily in C2. So these are examples of 4-dimensional symplectic manifolds. The ellipsoid, it comes with 2 parameters. So it's kind of like an egg shape in C2. And it has the property that if you intersect it with the first complex plane, you'll get a disk of area A, and in the second, a disk of area B. And the polydisk is merely a product of the 2 disks inside C2. So these are essentially the symplectic manifolds that we'll be dealing with today. So, whenever we talk about a new mathematical object, you'd like to describe when you have an equivalence of the 2. So in group theory, you might have an isomorphism of groups in a way to make sense of equivalence of groups. We have the same thing for manifolds and symplectic manifolds. So to do so, we'll first describe what a diffeomorphism is. It's kind of like an amped up homeomorphism. It's one for which it's a smooth bijective map with a smooth inverse between manifolds. And we can amp that definition up again for symplectic manifolds. So do symplectic manifolds, X and X prime, are symplectomorphic when we have a diffeomorphism that respects the symplectic forms. And so what you're seeing right there, you see F star or F pullback of omega prime. This provides a 2 form on the target, on the base X, and to compute what that pairing is, to take 2 vectors on X, you compute by pushing forward the vectors via the differential and pairing them on the image. So that's how you compute the pullback, and we call such a diffeomorphism a symplectomorphism. Okay, and so we'll define what a symplectic embedding is, which is, in the title of our talk. So a manifold, a symplectic manifold X, symplectically embeds into another one, X prime, if there's an injective smooth map or an embedding F of X into X prime, such that F is a symplectomorphism onto its image. And you should kind of think of it as, if you do have a symplectic embedding, you have a copy of X inside X prime. So whenever you have a symplectic embedding, you should think of X prime as the bigger symplectic manifold. It has more volume in a sense, because symplectomorphisms preserve that omega, they're also going to preserve that volume. So symplectomorphisms are necessarily volume preserving, but in the Venn diagram of smooth maps, we have symplectomorphisms inside the ones that are volume preserving. But is it complete containment, or is it a little bit bigger? That's a good question to ask. We can go to the.
Oh, sorry.
Yeah, we can answer that question. Actually, we've got a good theorem that kind of explains this relationship. It's a celebrated result from Gromov from 1985. And this theorem tells us precisely when we have a symplectic embedding of the ball into a cylinder. So the ball of parameter little r, we've got the cylinder of parameter capital R. Well, what this theorem says is that we're only guaranteed to have a symplectic embedding of the ball into the cylinder whenever we have this inequality of parameters, when little r is less than or equal to big R. And you should note that if we do have this inequality, then you can always obtain such an embedding by merely including the ball into the cylinder. You're not doing anything wonky to the ball. It naturally just sits inside the cylinder. So you can always obtain it that way. Now, on the other hand, essentially, if the cylinder's smaller and the ball doesn't sit within, you can ask yourself, is there a symplectic way to push this ball into the toothpaste, into the tube of toothpaste? But This theorem says you cannot do so. And the theorem is, the proofs are pretty difficult, and they rely on looking at solutions to nonlinear elliptic PDEs, geometric PDEs. And this is a cool result because it's one of the only instances in which we have results on symplectic embeddings for dimensions greater than 4. So lots of what we know really is restricted to 4 dimensions. And now I'm ready to go to the next page, Joe, thank you. So we'd like to kind of know when symplectic embeddings don't exist. It's kind of hard to say when one doesn't exist. And so the idea to use here is capacities. So the Gromov width actually turns out to be an example of a capacity. So let's just talk about the Gromov width. The Gromov width of a symplectic manifold is the sup, or the least upper bound of all real numbers R, such that you have a symplectic embedding of the ball into that X. So the previous example just tells us that the Gromov width of the cylinder of I don't want to say capacity, the cylinder of parameter R is R itself. And symplectic capacities are going to provide examples of ways that we can obstruct symplectic embeddings. So let's describe what a symplectic capacity is. The Gromov width turns out to be one of these. You can think of a symplectic capacity as a kind of measurement. It's a function. So what you do, you input a symplectic manifold, you put it in, and out pops a number. And you should think of that number as like a measurement of the symplectic manifold that you put in. It's sort of like the size in a certain sense. It's not the volume, but it's a certain size of the manifold that you started with. It's a measurement. And it has to satisfy 3 properties. So the first one is the most important one that we'll be dealing with today, monotonicity. If you do know that there's a symplectic embedding of X into another manifold, X prime, as I said previously, that you should think in your head that that makes X prime like the bigger symplectic manifold, then you better have an inequality of the capacities of those 2 symplectic manifolds. Like X prime is bigger in some sense. It has a bigger measurement. Now these other 2 properties are important. We have a scaling, sort of a linearity property. You can always rescale a symplectic form by a non-zero number. And so your capacity better respect that scaling in a certain sense. And then there's a normalization, a weak normalization property that says your capacity of the ball better be less than or equal to the capacity of the cylinder. Okay, so we actually have there's some pretty cool results regarding symplectic embeddings of ellipsoids. So remember, our ellipsoids are 4-dimensional manifolds, and they're within C2, and they come with 2 parameters. So in order to describe when we'll have a symplectic embedding of one ellipsoid into the other, I should describe this sort of mysterious sequence that you can build out of any 2 positive numbers, positive real numbers. So to make this sequence N, you will look at every non-negative integer linear combination of the 2 quantities A and B. So you get this big old array of real numbers, and you will arrange them into a sequence, in a non-decreasing sequence. And you want to keep track of multiplicities. So you have this long sequence of numbers, and that's the sequence associated to those 2 parameters. Now, a theorem from 2011 by Dusa-McDuff demonstrates that you'll have a symplectic embedding of EAB into ECD if and only if you look at the 2 sequences that you get from those parameters, and term by term by term, you have pointwise boundedness in those sequences, which is kind of a crazy result, which is pretty cool. So for this reason, you can show that you'll have a symplectic embedding of E14 into E22. And it kind of turns out that we learned that Michael Hutchings realized that the kth term in this sequence actually turns out to be a symplectic capacity applied to that underlying ellipsoid. That's kind of the magic that's underlying all of this stuff. And I think that's what Morgan is slated to talk about in the next slide.
Okay, thanks, Leo. So, right, so there's this sequence that you can associate to a symplectic 4 manifold called its ECH capacities. And that sequence starts with 0, and it's indexed by the natural numbers, and C1 is always greater than 0. C1 is also a symplectic capacity, as Leo defined them. And then the higher terms C2, C3, et cetera, form an increasing sequence that increases not necessarily strictly, and maybe one, and then once one is all the terms after are infinity. And the terms for C2, C3, et cetera, are also symplectic capacities, but they don't satisfy the weak normalization that Leo discussed. So they're almost symplectic capacities essentially. And the point is, these are kind of a more refined way of looking at obstructions to symplectic embeddings than just perhaps a single symplectic capacity. And so we're going to sort of explain how these work, and then talk a little bit more about other obstructions, maybe that inspired by these obstructions, which Hao and Yirong will tell you how to use to obstruct more complicated symplectic embeddings. So, so how do you get C sub k of the ellipsoid? It's the smallest number L, such that k+1 lattice points are contained in the region in the figure. So it's the region in R2 bounded by the line ax plus by equals L and the x and y axes. So you can see that when ax plus by is equal to, so it should be bx plus ay is equal to, it should be bx plus ay, because then in this case you would have L equals to ab. Anyway, so you can see that this line of slope, basically the idea is that there's a line of slope negative a over b, and as you move the line to the right, it includes more and more lattice points, and you can label each of those lattice points by its coordinate, its x coordinate times b, or times b plus its y coordinate times a, and those labels will form the sequence that Leo told you about on the previous slide. So then as you increase this number L, you're going to include more and more lattice points into that triangle, and as you pass a lattice point, that will be the kth ECH capacity. And in general, there are more complicated formulas for ECH capacities. The most important property is what I put in blue here. Oh, sorry, on the previous slide still. Is that if you have a symplectic embedding from x omega into x prime omega prime, then the kth ECH capacity of x omega is at most the kth ECH capacity of x prime omega prime for all k. So this is what Leo told you about for the NAB sequences, but in general. Okay, next slide. Thanks. Okay, so some properties. So the contrapositive of the blue formula on the previous slide is just that if you have a symplectic, or if you have an inequality of capacities, so if one capacity of x omega is greater than a single capacity of x prime omega prime, then x omega cannot symplectically embed into x prime omega prime. So that means that basically you have something that could possibly be easy to check. You just need to check two numbers, and if one number is bigger than the other, then you don't have an embedding. We can reprove four-dimensional Gromov non-squeezing with these numbers, because the first capacity of the ball is the parameter of the ball, and the first capacity of the cylinder is the parameter of the cylinder. And we use our blue equation. The next thing I wanted to mention is that the ECH capacities actually record the volume of a symplectic manifold. So in that sense, they tell you one way in which symplectic geometry is kind of stronger than volume preserving geometry, but in the limit, you sort of just obtain the same obstruction that you would get from requiring the volume of the manifold you're embedding to be at most the volume of the manifold you're embedding into. So this formula isn't really important, but the important part of the formula is just that there is some limit you can cook up using capacities that gives you back the volume. So the final thing I wanted to mention on this slide is how we get these capacities in general, not just for ellipsoids. So what the kth ECH capacity actually is it's the area of a surface in X measured using the symplectic form omega that solves some partial differential equation, as Leo mentioned, which we'll refer to as a J-holomorphic curve partial differential equation with a fixed boundary condition. And the boundary has to be on the boundary of X. And so we get the blue equation that an embedding implies the inequality of capacities because properties of ECH, which is this which is the theory in which ECH capacities live, force the surface in the larger, so I have my smaller manifold embedded in my bigger manifold, and I have some PDE that determines, that says, okay, I need to find the omega area of the solution to some PDE in the smaller manifold, and the omega area of some solution to the PDE in the larger manifold. And it turns out that certain properties of ECH make the solution in the larger manifold agree with the solution in the smaller manifold when it sort of passes into the smaller manifold. So that's why the area of the area of the surface in the larger manifold has to be bigger than that in the smaller manifold, or at least as large as that in the smaller manifold. And this same sort of idea implies the action inequality, which is something you'll hear about from Yirong later. Okay, so let's talk about the examples that Leo introduced earlier in the talk. And we're going to use, we're sort of going to think about them in a different way that will allow us to understand their symplectic geometry better. So if I have a polytope omega in the first quadrant of R2, I can define x omega as just being all pairs in C2, pairs of complex numbers, where pi times the modulus of z1 squared, comma pi times the modulus of z2 squared is an element of the polytope omega. So I can recast the ball, the ellipsoid, and the polydisk, and actually the four-dimensional cylinder as well, although we're not really thinking about that example throughout the rest of the talk, as x omegas for the omegas that I have on the bottom of the slide. So the ball is x omega, where omega is an isosceles right triangle with side length A. The ellipsoid is x omega, where omega is a right triangle with side lengths A and B. And the polydisk is x omega, where omega is a rectangle with side lengths A and B. And these x omegas, what their name is, they're called symplectic toric domains. So the reason why they're called toric is because if you look at any point in omega that's not on the axes, then you have in x omega, there's a whole torus that sort of projects to that point of values z1 and z2, where pi z1 squared, pi modulus of z1 squared, comma pi modulus of z2 squared is equal to that point in R2. So I guess one other thing to mention about these pictures is you should sort of nestle these pictures up against the axes. So the bottom left corner of all three of these pictures is the origin. Okay, next slide, please, thanks. Okay, so recasting our manifolds in this light helps us understand embeddings of the toric domains. So the first thing is, if I compute the volume of x omega, that's actually just equal to the area of omega, which is really helpful. And I suppose another thing that's sort of even more obvious is if one omega fits into another omega, then x omega, then the x omegas also fit. So that's another way to construct symplectic embeddings. The second thing is, in some cases, we can actually compute the ECH capacities from the geometry of omega. So we had this triangle with this moving line, which told us how to compute the ECH capacities of the ellipsoid. And so in this figure on the right, there shouldn't be any PAB. That's a typo. I apologize for that. So in the caption of the figure on the right. So the thing to notice here is that the slope of this line, or this triangle that determines the ECH capacities on the right, looks very similar to the triangle that determines the ellipsoid on the left. So that's a story that continues throughout the subject. You can generally compute the ECH capacities from the polytope omega. So, and then the rest of our talk will be even more ways to obstruct embeddings of x omega using the combinatorics of omega itself. And next slide, please. So this is easier in some cases than in others. So if omega is the space in the first quadrant under the graph of a function, that's what the first line, a non-increasing function, that's what the first line says. And this space is a concave region, meaning that the function is convex, then we call x omega a concave toric domain. Otherwise, if f is a concave function, then we call x omega a convex toric domain. So the terminology is confusing, but when you see pictures, it will make sense. So in generalizing McDuff's work, Christopher Gardner proved that if the domain is concave and the target is convex, then this blue equation that we've sort of been carrying with us throughout the this section of the talk is actually an equivalence. So we know the sort of rightward pointing arrow. We know that if we have a symplectic embedding, we get the inequalities of capacities, but in some cases we actually get an equivalence. But if our domain is not concave, then we need other means to obstruct symplectic embeddings because this blue equation doesn't work. So for example, polydisks, I put the definition of convex and concave there again. Polydisks are convex, they're not concave. And you can sort of, if you apply the, so for a polydisk, it's a little bit sort of an edge case, but if you were to like round the corner a little bit, then you would see that it would fall under the definition of a convex toric domain, even though the function defining it is concave because it's a convex region in R2. So what Hao and Yirong are going to explain is how to use the combinatorics of omega beyond just the ECH capacities of omega to obstruct symplectic embeddings of polydisks into ellipsoids based on the relationships between the parameters defining those spaces.
Thank you, Morgan. Before I get into our results, I would like to give a little bit more context to the problem that we're dealing with. I'll do this by showing a known result by Hutchins. This result says that suppose A is between 1 and 2 and B is a positive integer, then the polydisk PA1 symplectically embeds into the ellipsoid EBCC if and only if this inequality here, A plus B, is less than or equal to BC. I have a few remarks about this result here. If we instead let A and B be any real number greater than 1, then this is actually the most general question we can ask about this sort of embedding the polydisk into the ellipsoid in 4 dimensions. This is because if we are given a polydisk and an ellipsoid, we can swap the 2 parameters of each of them independently without changing the embedding problem. So if you ask, can PAB embed into ECD, then it's the same question as asking, can PBA embed into ECD, can DAB embed into EDC, and so on. So this means we can assume without loss of generality that in both the domain and the target, the first parameter is larger than the second one. Another thing we can do is to scale all of our 4 parameters at the same time by the same constant. This won't change the question either. So therefore, you can do all of these changes as necessary to turn the embedding problem that you have into this sort of thing that we have here, into PA1, into EBCC. And people do that because the 1 here will make computations and proof writing a little bit easier. Second remark, what does this A plus B less than or equal to BC mean? It just means that the polytope of PA1, which is the blue rectangle here, sits inside the polytope of EBCC, which is the green triangle. And at the manifold level, this means that the polydisk can be included into the ellipsoid, and the inclusion is a symplectic embedding. So in this case, if we have this, then we get the embedding for free. What's really interesting is the only if direction of this statement. It means that if PA1 embeds into EBCC, then it can also be just directly included into EBCC. This is very strong requirement, and it shows the rigidity of symplectic embedding because it says that under certain conditions, the trivial inclusion is the best thing we can do. Finally, you can see that this result is for A between 1 and 2. This is because when A gets greater than 2, the symplectic embedding actually starts to get flexible. And there is actually a construction of embedding of PA1 into BCC of EBCC when A is greater than 2 using a method called symplectic folding, which is due to Felix-Schlenk. So this result makes us wonder, if B is not an integer, does the if and only if statement still hold? So indeed, we got something when B is a half integer, and here's our result. So if D0 is a fixed odd prime number, and A is between 1 and 2D0 minus 1 over D0, C is any positive real number, and B is equal to P over 2 for some odd integer P greater than or equal to 4D0 plus 1, then PA1 embeds into EBCC if and only if A plus B is less than or equal to BC. So note that the if and only if statement is the same as the one before, and the hypothesis we have, though the hypothesis we have look less straightforward than the one from the last slide. So to give you a better idea, the plot here shows that the upper bound for A and the lower bound for P for the first 4 values of D naught. The gray area is the area where the theorem works. So for our result, A isn't all the way to 2. There's a good reason for that, and how we'll probably explain it to us if time permits. And as P gets larger, the statement works for more values of A that gets really close to 2. So to give you a picture of what that means geometrically, remember that our ellipsoid is EBCC, where B is P over 2, and as P gets larger, B gets larger, and the ellipsoid gets longer and skinnier in its shape. So if it has to satisfy A plus B less than or equal to BC, when the shape of the ellipsoid gets skinnier, the theorem tells us that it's harder for the polydisk to be embedded into the ellipsoid. In the sense that what we can provide, what we can provide, we can provide sharp obstructions for more values of A. So this theorem only gives us information about P greater than or equal to 13. Can we say anything for smaller values of P? The answer is yes. We have similar results here for when P is an odd integer, or P is an odd integer greater than 7. But when P gets greater than or equal to 13, the theorem from the last slide is always stronger than these two we have here. Next slide, please. Now I would like to introduce the combinatorial tools that we need to prove our theorem. I'll start with the definition of a convex generator. A convex generator looks something like the ones in the figures here. There are graphs in the first quadrant of a piecewise linear non-increasing concave function. Sometimes we'll add vertical segments to the right of the graph, and the vertices of this graph should always be at the integer lattice points. We label each of the edges to be E or H, but we can only use E to label horizontal and vertical edges. Here, the two figures actually represent the same convex generator. Most of the time, we like to write the edges in a more detailed way, as in the figure to the right. And this is actually called a formal product. So we write lambda equals to E10 to the third, E32, H32. And the 32 just means, just gives the displacement vector for that edge. The formula in the second definition will be very useful to us. This is called the ECH index of a convex generator. Here, L of lambda means the number of lattice points enclosed by lambda and the XY axes, including the ones on the boundary. And H of lambda just means the number of edges of lambda that's labeled H. So in this example we have here, H of lambda is just 1. Next slide, please. Another extremely useful piece of information about convex generators is their symplectic action with respect to different toric domains. The action actually changes, so it depends on the toric domains we are considering. And in general, it's not very straightforward to compute, but luckily the actions of a convex generator with respect to the polydisk and the ellipsoid can be directly computed with the formulas here. Our proof also uses convex generators that are minimal with respect to the ellipsoid. You can see the definition of a minimal convex generator here. We'll consider the generator EP2 to the D naught, which is minimal for the ellipsoid for any positive real number C and and positive integer D naught. The last thing I would say about the convex generator is that, in fact, if a generator is minimal for a toric domain and has index 2k, then its action with respect to this toric domain is equal to the kth ECH capacity of the toric domain, which is introduced earlier by Morgan. The last definition we will need before getting to the Hutchins criterion is the idea of when one convex generator is less than or equal to the other. This will naturally depend on the domain and the target of the embedding that we're considering. So if we have two generators, lambda and lambda prime, then we say the first one is less than or equal to the other with respect to PA1 and EBCC, if it satisfies the 3 requirements here, which we call the index requirement, the action inequality, and the J-holomorphic curve genus inequality. So here in the third inequality here, x of lambda and y of lambda means the x and y intercept of lambda, and m of lambda prime means the multiplicity of lambda prime. So for example, if lambda prime is written as the formal product e10 to the third e32, then the multiplicity is their exponents added up together. So in this case, it will be 4. And this third inequality here is actually the most worth noting because it carries additional, more refined information to what ECH capacities alone can tell us. And incorporating this, this condition into the whole machinery, this allows us to provide better obstructions than just using ECH capacities alone. Next, how we'll introduce the Hutchings criterion, which is the key ingredient to our proof.
Thank you very much. So yeah, like Yirong said, now we'll try to introduce the key machinery that we will use to provide our theorem. The Hutchings criterion written here states that if we have a symplectic embedding from one convex toric domain, x omega into another, x omega prime, and that if we look at a minimum convex generator lambda prime that is associated to the target of the embedding, then the embedding guarantees the existence of a convex generator lambda that is associated to the domain that's satisfying the following list of properties. So rather than to bore you with the combinatorial details of these conditions, I'll just say this. So geometrically, what is going on is that when a symplectic embedding exists, in the cobordism of the boundaries of the two convex toric domain, there exists certain irreducible complex curves. And the technical term we use for these curves are J-holomorphic curves, which I believe Leo talked a little bit about before. And each of these J-holomorphic curves connects figuratively, but also literally if we include some caveats like perturbing the boundaries, it connects the factors in the product decomposition of lambda and lambda prime that is written here. So lambda equal factors into n different convex generators and lambda prime into the same into the same number of convex generators. Now, studying these curves give you a set of necessary conditions on the associated convex generators. In particular, this lambda I is less than or equal to lambda I prime in the context of bullet point 1 is one of the necessary consequences of the existence of the J-holomorphic curve. Since once you have this setup, the inequalities that are introduced by Yirong in the previous slide can simply be derived from, for example, or they're not simple, but they can be derived once you have the setup from facts about ECH capacities and facts like Stokes theorem and facts that J-holomorphic curve must have non-negative genus. Now, what is truly amazing, at least to us undergrads, is that to provide obstructions, we don't have to fully understand and worry about the details of J-holomorphic curve techniques because this powerful machinery is formulated in a completely combinatorial way. I will now try to demonstrate. So we take our domain x omega, apply specialize it to just PA1, the polydisk, and take x omega prime, the target, to be just the ellipsoid EBCC. And I will try to demonstrate, or rather provide a sketch of proof to how we're going to obtain the results that's stated in the embedding theorem earlier. And I'll try to mention a little bit where each of these conditions will become useful. So here is again the statement of the theorem to refresh your memory. So like Yirong mentioned before, the inequality a plus b is less than or equal to b1 holds precisely when you look at the rectangle representing the polydisk, and it sits inside the triangle representing the ellipsoid EBCC. So when this inequality holds, we can trivially include the domain to the target, no problem. Now the key is the other direction, and in that direction, what we are going to do is that we can use Hutchings criterion in its contrapositive form to exclude any possibility of a symplectic embedding from PA1 to EBCC when A plus B is in fact greater than BC. So to apply this method, remember, we need to take a convex generator that is minimum for the target. So we take lambda prime to be EP2 to the D naught for a fixed prime D naught, which Yirong introduced this minimum. And Hutchings criterion tells us there should be a lambda associated to the polydisk, and together it comes with a product decomposition. What we're going to show is we're just going to write this product decomposition, consider all of the possible cases into these 3 cases and eliminate each one of them, yes, using the combinatorial inequalities. So proceeding as planned, we need to first show that there just cannot be any lambda is less than or equal to lambda prime in the definition that Yirong gave earlier. So we split this further into 3 cases according to the y-intercept of lambda based on their distinct combinatorial features. And I'll just only say a little bit about what information gets used in which step. So the red one can be eliminated as an immediate result of the action inequality combined with the index requirement. It's not very interesting to talk about. What's more interesting is the green and the blue cases. So if we consider if the y-intercept of lambda is rather small, like drawing the green cases, then the ECH index requirement, which remember, as Yirong introduced, is directly related to the number of integer lattice points that sits underneath the graph of the generator. So the ECH index requirements forces the x-intercept to be large because the x-intercept of lambda to be large because lambda needs to enclose roughly the same number of lattice points as EP2 to the d naught, which we have taken to be lambda prime, right? And this forces, so in this case, the restriction on lambda is x lambda is powerful enough that once we plug this into the action inequality, the restriction on x lambda is powerful enough that we can manipulate it to get some information on A, and we can conclude that the green case cannot happen when A is smaller than 2d naught minus 1 over d naught, which is precisely stated in our hypothesis. So for the blue case, the ECH index requirement is no longer as useful as y lambda gets large. This is important to note that if we were just to use information coming from ECH capacities like Morgan introduced, and we have to somehow first translate it into this combinatorial setting. But if we were just to use these information, we would not have been able to eliminate the blue case. And we will instead, like Yirong remarked, we use the J-holomorphic curve genus inequality, which contains additional information to the ECH, to eliminate this case and get a similar bound on x lambda that is just as powerful. Yes. So in the next case, we can actually carry over the argument from the previous slide with only minor modification in the case where we have k factors where k sits between 2 and d naught minus 1. So this is actually where the primality of d naught becomes very important. We can no longer rule out just right away the possibility of any lambda I less than or equal to EP2 to some d, where d is less than or equal to d naught, but we can restrict its possibility significantly. We were managed to show that if indeed it's the case that lambda I is less than or equal to EP2 to the d in this setting, then the convex generator must always contain an E10 factor when we write it out as a formal product. This is where, so we use the primality of D because the second condition of Hutchings criterion asserts that if any pair of the factor, lambda I and lambda j, shares an elliptic orbit, in this case E10, then not only is lambda I forced to be the same as lambda j, but we also have lambda prime I forced to be equal to lambda prime j, which means that we look at the product decomposition of lambda prime, which is just EP2 to the d naught. Its factor can only look like EP2 to some integer power di that is less than d naught, right? But all of the di must be the same because all of the lambda I shares a common E10 factor. And this is impossible because you cannot have di times k is equal to d naught when d naught is prime. And k is strictly between, k is between 2 and d naught minus 1. So in the last case, where we actually have d naught different factors, so we factorize each lambda prime into each individual EP2 to the 1. We actually only need to categorize lambda I when it's less than or equal to EP2 to the 1. There is no trick here, and explicit index computation using the third bullet points of Hutchings criterion can finish the proof for us. So like Yirong remarked on earlier, I would just only talk about this briefly because we're almost out of time. So Yirong remarked earlier, right? Our results puts ugly requirement on A and P. It's not as simple as we would have wished it to be. So yeah, we will be very happy if the condition is something like A is between 1 and 2, and there's no restriction on P. But actually, using this method, this is the best that we can get in the following rigorous sense. So in this example, we can actually, so if we want to increase the bound on A by any positive amount, we can actually show that there always exists a convex generator lambda less than or equal to EP2 to the d naught for any single d naught greater than or equal to 2, not just prime. So if we want to use Hutchings criterion to provide a contradiction looking at this generator, then what this is saying is that no matter how we manipulate the inequalities, such thing always exists, hence we can never arrive at a contradiction. And in a similar sense, as on the next slide, the value of P cannot actually be lowered by any amounts. So I know here it says that if we lower P to 4D0 minus 3, but it's just because it's more convenient to write things out. So it's in a similar sense, we always have this example and we can never provide obstruction if such example exists. And I will not go over this example in detail for the sake of time. So I will leave you with a remark on some potential generalization of this result. So if we consider the case that, you remember, we're trying to study the embedding problem PA1 into EBCC, you consider the case where B is P over Q for integers, of course, PQ and and Q greater than 2. And if we still want a similar condition on A that limits to 2, like 2D0 minus 1 over D0, then we can actually provide explicit example that satisfy the Hutchins criterion, just like before in the 2 previous examples, which is saying that we have no contradiction and no obstruction. And it might still be possible to show some analogous result by restricting, putting even stronger restriction on the values of A, which is kind of undesirable. Or, this can inspire us to look to improve the machineries that already exists. So yeah, thank you very much.
And
Are there any questions?
here, I'll